Hi, welcome everybody. Today we are going to resume our discussions on MetroPT-3 Predictive Maintenance Project. And as you all are aware that we are implementing AI manager skills across this project. We already had a discussion in last two sessions about what all AI manager skills we will be discussing. And we will be implementing all those skill sets along with this realistic Metro PT3 predictive maintenance dataset. So basically, this study is divided across these five to six phases. And the very first phase starts from discovery phase. Then we have to ensure governance. We will be designing a solution. We will be delivering a solution for an enterprise. And finally, we will observe how we are going to ensure smooth operations and scaling in that enterprise environment. So this is what, as an AI manager, we have to take care of about the AI project. So typically, an AI manager is responsible for problem discovery phase, governance phase, design phase, delivery phase, operational and scaling phase. So he should have a end-to-end monitoring around it. Okay. Now, so what are we taking care? So here is the architecture of the project, okay, which we will be implementing. So initially, the project starts with a data set given. Okay. So as I have already told you in the previous session that we took this Metro PT3 sensor data set. And what I have done, I have uploaded a copy of that data set on Google's BigQuery. So the storage is available on BigQuery. Okay. Now, what we have to do is we have to get this data from BigQuery and we have to represent it in a clean view. This is our first requirement. Okay. Once we have the clean view available, we are going to convert this data set into a 1 minute feature table. Okay. So that every minute we get data across different set of features which we are observing. So this is what we have to achieve, which means we have to first we have to clean the data. Given the data set, we have to clean the data first. We have to pre-process the data so that we get the appropriate features for the relative time window for which we would want an analysis to be done. Because here we will be implementing an analysis on a live machine at production. So we want a quick, a faster interval feature table available with us so that whatever data is coming is updated and we can predict any issues or we can predict the anomalies right on time. This is what is the requirement. Once we have the appropriate feature table ready, which we will use in order to predict the anomalies, then we do need to implement one model, okay, a machine learning model, which can learn through these features and predict anomalies for us. This is what we are going to implement. So what are we going to do? We are going to implement rules and isolation forest. These are the algorithms which we will understand and we will try to implement them in order to learn features and predict anomalies. This is what we will be doing. Once we have an isolation forest at place, we will be raising alerts. Okay. Now, these alerts will be persistent alerts, which means as soon as an anomaly is detected, an alert will be raised via the system, and that alert will be sent for a human review, okay, for a human feedback. So a human would get an escalation report or let's say an email or an alert, and on the basis of that alert, the human is going to take respective action. Okay. Similarly, monitoring can be done by, let's say, humans or with other monitoring tools. And we shall be calculating model drifts. Okay. In case if the model drift scores are going below the thresholds, below the fixed thresholds or an automated thresholds, which we might be learning. So depending on that drift, we are going to retrain the model. Okay. So if weaknesses weakness is identified or low accuracy is identified, if the model drift score goes low or it crosses the threshold, depending on the threshold, whatever threshold we have set, we are going to retrain the model. Okay. So the isolation forest model will retrain, and eventually, again, it will start producing better results. And with a human acknowledgement, we will be improving the system. Okay. So this is an end-to-end architecture of what we are going to implement around this particular project. So we are going to get the data set, we are going to clean it, we are going to pre-process it, we are going to make it ready for a feature table. Then we will give that table to, we will apply models on those tables. Once the models produce appropriate accuracy, we will be raising alerts using those models. A human in the loop or a human feedback would be taken in order to verify those alerts. And depending on actual alerts or depending on more failure alerts, in case if there are more false positives and the model drift score is going low, we are going to again retrain the model continuously so as to improve the performance of the system. So this is the end-to-end architecture of this particular project. Okay. Now, so we are going to implement it, and we are going to implement these in a phase-wise manner. So there are 6 phases in this. So if I tell you basically, an AI manager has a specific life cycle and an operating model. Okay. So as we join as an AI manager at an organization, we shall implement our AI manager lifecycle in order to ensure and in order to check whether the AI systems is appropriately working at place, and we shall be able to integrate with the existing environment. Now, what is the significance of this life cycle and this operating model? The significance is this is a structured way to help move from business problem to a reliable production service. Okay. So with this AI manager lifecycle of discovery, governance, design, delivery, operations, and scale, we are going to move from an identified business problem to a reliable production AI service deployed at production, and users are using it. So these are the 6 phases which we shall remember: discover, govern, design, deliver, operate, and scale. Operate and scale. Okay. Before I move further in this AI manager lifecycle, I would like to take you to I'll take you to our interview studio, and I'm going to show you how this issue looks like at production. Okay. So before we get into this, I would like to give you a quick interview story across this, and then we are going to implement it. So this is for your reference, and I'm just increasing the size of it so that you can see.
A plant installs the pipeline on a compressor APU. Sensors stream motor current and pressure to the model. One day the model sees a small but consistent rise in motor current and a subtle pressure ripple. It marks the pattern as anomalous and alerts the maintenance supervisor with a chart and recommended checks. A technician inspects the unit and finds a worn valve seal. The team replaces the seal during planned hours. A major failure is avoided. The event is logged and used to refine the model thresholds. Over time, the plant sees fewer emergency repairs and more predictable maintenance windows. This closed-loop approach ties sensor data to action and continuous improvement.
So when we begin this AI manager journey, we have identified that for an AI manager, the major objective is continuous improvement of the system. Okay. Now, so suppose we are already working, let's say, with Hitachi Digital in this particular use case, but the data set which we took is for MetroPT-3. So as we see, that let's say there is a system at place. There is an AI system which is already working there, which you have already deployed. So this interview story is relating to that. There is an AI system already at place. Okay. And what that AI system is expected to do. So it is expected that already these sensors, are streaming motor current information, pressure information to the model. So let's say there is a model, and this model is this isolation forest model, which is already at place, and it is getting this information around about current, pressure, and various other features. Okay. So eventually we are going to collect these features, and we have to make a 1 minute, feature interval table. So that feature table will be given to model in order to get that model trained appropriately. Okay. Now, the model is going to detect anomaly. So we observed here that suddenly one day the model was seeing a consistent rise in motor current and a subtle pressure ripple. Okay. So since uh, so on that air production unit, a sensor was already deployed or connected, and that sensor was obviously constantly it was monitoring the pressure and current around it, and it was sending that data to that respective model, and due to that the model started detection of this unwanted current or consistent rise in that motor current that is identified. Okay. Now that is an anomaly which happened because generally, let's say the pressure and the current would be in a regulated range. In case if that regulated range is overlapped or bypassed, obviously that is an anomaly. And with this constant data coming in at every second or let's say at every minute, and it is easy for an AI model to quickly identify the pattern, and in case if the pattern is crossing the normal regular pattern. Okay. Now, so once that pattern or an anomaly was identified, the alert was generated, and automatically an escalation message or a pressure reading message or an alert message has been sent to this maintenance supervisor or whoever was in that user category as per the stack. So once that is done, the technician inspected and he found a worn valve seal. So they found out the issue, and due to this, what exactly happened? The team replaced the seal during the planned hours so that so the pressure and current obviously came normal again, and a major failure which could have occurred is avoided. So practically at a place where there was an AI model running who was constantly reading the sensor data, was alerting people. Once that alert has reached to a manager, he has asked somebody, a technical person, to go there, check the system. He found out, okay, there is some problem with the seal. He replaced that seal. And with that, a failure was avoided. Okay. So now this complete event is obviously being logged constantly. And due to this, okay, these logs which are being generated, these logs help refine the model thresholds. Okay. That what whenever a human confirmed, the human technician confirmed that yes, there was a problem, and these current metrics which were showing above the average were actually the anomalies, and this event must be recorded, and this should give a signal back to the model that yes, this is a condition where a failure or an anomaly is approved by the system. So eventually the system will learn, and it will improve the accuracy of confirmed prediction of some anomaly happening. So similarly, over time, let's say with a period of, let's say months and years, eventually this data would be available to that particular model, and the model would be able to learn more and more about such factual events where a technical or a human in the loop is already approving, okay, such incidents happened and there were certain actual issues were identified. Through this, the model can be improved constantly. Okay, so I believe so why I have narrated this kind of situation with you is just to have you a clear understanding of the architecture, that how that system is working. So at one end we have a system which we are designing where we are collecting some data, we are cleaning it, we are processing it, we are making a feature table out of it, we are running a model on it, and we are raising those alerts. But how that system is integrated with an actual scenario, so in order to relate that, okay, so I believe this end-to-end architecture is clear to you, I believe.
Yeah.
Okay, great.
Yeah, totally.
Okay, now on the basis of human feedback, we will be continuously monitoring the drift scores. In case if they go low, we will fine tune the model and retrain the model again with the new events and new data coming into the system. Now, so why this would help, and why an AI manager would be useful for organizations. So typically, it is not just about building an AI model. Obviously, while you are working at a system, there are certain phases to it. Designing an AI system is only one such part out of it. Okay, but ensuring the right stakeholders are getting that right kind of information and appropriate governance is happening across the model. Delivery, operations, and scaling is also being supported. So that is the role of an AI manager who has to implement these phases for any specific project at an organization. Now, so coming back to the next part, so this it prevents a technically impressive model from being built without clear users, controls, ownership, or measurable business value. Okay, so the major objective of an AI manager is to identify what impact would this AI solution will create, what problem of the business or the customers it is going to solve. Okay, who would be responsible, who will own the who will have the accountability of the outcomes if the failures happen, or if there is a system at place which is helping such failures, preventing such failures. Then ensuring AI is in control appropriately. It is not hallucinating, it is not showing biased responses, so such control has to be implemented appropriately. Then everything here starts with a customer experience, and that is what is important. So customer experience as in the user experience, who's going to use it. So the alerts have to be in such easy to understand format, so that any non-technical person, eventually they might be technical but they might not have clear communications, they don't have that level of communication skills, where it might be difficult for them to understand what kind of AI system is implemented and what it is responding. So it has to be in a easy to understand manner depending on who's going to use the systems. Okay, now so this is what we are going to implement. So what are the users in the project? So we are going to implement a notebook, a Python notebook, where we will be implementing these business objectives, governance checks, BigQuery design, anomaly models, monitoring, and continuous improvement. So these are the phases which we will be implementing on a Python notebook step by step, so that we get a little more idea and control about how things are happening, and validate that each phase has named owners, deliverables, decision gates, and measurable exit criteria. So this is the objective of our AI manager, who has to validate and measure all of these 6 stages. Now, so what are we going to do now? We are going to implement predictive maintenance across it. Okay. So for this predictive maintenance, we will be using sensor data. And this sensor data will be used to estimate abnormal degradation. Okay. And the objective is to estimate it early enough to schedule maintenance before a failure or a high stress event occurs. Okay. So that we can schedule maintenance events appropriately right on time. Okay. This is what is required out of this. And wherever in the document or in the code, wherever PDM is used, that stands for predictive maintenance. Okay. Now, this predictive maintenance will help us reduce emergency repairs. It will help us reduce downtime. It will help us uh, address asset stress issues in case if there are limited assets, and if some of them may go down, it will eventually impact. So this matters. Similarly, it helps us prevent service disruptions. This is also very, very important. Now, in this particular project, in this MetroPT-3 data set, we are using data which will show us, values for compressor pressure. We will read current, we'll get temperature, and we'll get valve signals. Okay, these are the features which we are going to receive from this MetroPT-3 dataset project, and we will be using these features to identify abnormal behavior. Okay, wherever the values will go, will become anomalous, will become out of range. Okay, or that behaviors will be identified, and a warning signal will be generated before any air leak event. So before the air leaks from the air production unit, from the APU, we have to generate a warning signal appropriately right on time so that a scheduled maintenance can be done of that system. So what can go wrong? There could be late or noisy warnings. Okay. And these noisy warnings can cause missed failures. Okay. There could be alert fatigues. It might be a possibility that the system may not be, accurately predicting the anomalies, and it might be alerting unnecessarily. That could happen. So we have to ensure that the AI system is trained appropriately so that it confidently alerts when there is a high probability of such failure, while protecting eventually in case if, let's say, there is a low probability of failure event, but the failure happens. So even with low probability, whenever there are chances of possible failures, the system should be able to generate the alerts appropriately. And whatever missing signals are there, we should be able to collect them as well. So this is what we are going to implement. Finally, we will be protecting ourselves from from unnecessary part replacements, as well as in order to protect ourselves from any unsafe decisions. So we have to have a predictive maintenance systems at place. And what we are going to do, so this will help us measure and validate whether our system is working perfectly. So we are going to measure event recall. We are going to measure warning lead time. We are going to identify what is the false alerts per compressor day, how many downtimes are avoided, okay, how many maintenance acceptance rate, what is the score on this, okay. So these are some of the measures which we have to calculate in order to ensure that the predictive maintenance system is working properly. So this is what we are going to implement. Okay, I believe this is clear. So for the data set, so for the data set which we are taking, it is a high frequency multivariate time series data. So this means there are many sensors from where the data is being collected. These sensors are measured repeatedly at short time intervals. Okay. So let's say within less than every minute, these sensors are measured and we get a latest update of the data. And since there are many sensors, there are multiple variables which are taken into consideration. And these multiple variables, you can also consider them as multiple features like current, pressure, okay, and various other which we talk about in the previous one here. So since we are taking, here it is. Yeah, so we are taking pressure, current, temperature, and valve signals. Okay. These are some of the features which are taken into considerations. Rest, we will quickly check what all other features are there, which we will be taking into consideration. So all of these variables will be observed together, and then on the basis of them, an anomaly would be, identified and created. And then we will try to make a realistic system around it in order to ensure that timely alerts are happening. Now, so these sensor values are, available across time. Uh, there are nearby rows which are not independent. Okay, so we have to ensure that proper ordering of data is maintained because the data which is coming is continuous in nature, and values might be measured with respect to very nearby rows which are available in that respective data set. Then so we have multiple compressor signals in this data set, MetroPT-3. This MetroPT-3 dataset has multiple compressor signals available. And what this project is going to do, first we are going to convert all these compressor signal into 1 minute windows, okay, while retaining the temporal patterns. Okay, so we will be preparing the data set in a way, so depending on however the data is coming from sensors, we are going to convert those sensors by ensuring that the temporal patterns remain as it is, but we will convert them into a 1 minute time window so that we can easily process these compressor signals. So 1 minute of batch slots would be done, and this machine would be, these sensors would be evaluated. Similarly, there could be issues like random splitting leaks. This could happen. This we will talk about as soon as we progress further. Where what could happen that neighboring observations can get into train and test sets. Okay, so if neighboring observations will be available in training and testing sets, eventually the test would look that the model is working perfectly or so. Such issues can happen. So it can make the performance of the model look better than what actually it is. So we have to ensure that while we will be splitting the data set into training and testing sets, so the testing set should not have nearby neighboring observations, because neighboring observations are very close to each other and they have an impact on each other. So similarly, we should have observations which are quite distinct, so that the testing and predictions can be done appropriately. So that we have to ensure, and that we have to implement all of this while cleaning the data set which we will be taking. So how we are going to validate and measure this high frequency, how we are going to process and ensure this multivariate time series data is converted in a right format so that AI analysis can begin in order to develop an AI model. Okay. So first we are going to check the timestamp order. We are going to perform sampling intervals. Okay. This will be done. We are going to identify gaps. Okay. So that appropriate splitting between training and testing can be done. We will check duplicacies. Okay. We will check sensor coverage and autocorrelation. So this will be tested, validated, and measured, and then the appropriate data set would be taken into consideration. Now we are going to get started with the Google BigQuery architecture. Okay. So what do we have here is, we have a cloud data warehouse. Google BigQuery is a cloud data warehouse. And currently, because these sensors produce a lot of data every second, obviously you need to have a bigger storage and a storage which can, communicate faster. So Google BigQuery offers you that architecture where you can use to store such time series data. You can query that time series data. It is like SQL, but it is for big data. Okay. You can govern large data sets with SQL. So this is one of the advantages of using Google BigQuery for enterprise use cases. Okay. Majority of these telecom providers, they use Google BigQuery. So because you have seen these telecom providers, they generate data every milliseconds because of connectivity. While this internet Wi-Fi packets are being transmitted, communication is happening in real time. So a lot of data is being generated. And I have seen various telecom providers using Google BigQuery. So similarly, in our sensor case, Google BigQuery is a good choice to use it as a data warehouse storage, which we will use in order to perform our analysis. So I hope you are aware with structured query language. Okay, so we will be using SQL. So on Google BigQuery, we can apply SQL. Okay, so structured query language can be executed in order to create, read, update, delete, search, and implement SQL queries. Okay. Also, we will be using a fully qualified name, which contains the project name, the table name, and there is one more, information which is taken. And using all this three dataset ID. So first is project ID, dataset ID, and table name. So these three IDs collectively create a fully qualified name. And using that fully qualified name, we get access to Google BigQuery's table. And then we can start querying that with SQL and we can get appropriate outcome and then we can start analyzing it. So it separates scalable data preparation from local Python modeling and provides auditable tables for operations. Okay. So basically, whenever you have a scalability issue, whenever you have a large enterprise issue and you have to prepare the data for modeling, so Google BigQuery is one of the best, in order to handle large storage of data. Similarly, our raw MetroPT-3 data stays in BigQuery. Okay. And the outcome would be that we are going to have clean views. We are going to have feature tables. We are going to have rule scores. We are going to have model scores. We are going to have alerts. And then we have monitoring snapshots. Okay. And all of these will be created with the help of all those 6 phases, which we discussed. Okay. And this complete data set will be governed and will be written back to Google BigQuery. Okay. So currently we have raw data on BigQuery, but once we create clean data, features table, scoring out of it, model scoring on them, different alerts coming in, different monitoring or drift detection, evaluations happening, everything will again go back to BigQuery. So hence you need, a very strong storage architecture, which Google BigQuery offers. What can go wrong? So unbounded scans can cost too much. Okay. There could be weak table naming. There could be permissions, reduced traceability issues. We are going to address all such issues as soon as we will be implementing the project practically. So there could be wrong location settings which can break the SQL queries. So we have to avoid such cases while implementing, while implementing SQL with Google BigQuery and extracting the information. So how we are going to validate and measure the data? We are going to measure the bytes processed. Okay. What is the query duration happening? How the partitions are being used. Okay. What is the table freshness? I mean, how often the data is updated into that table? How many number of row counts we have? Okay. Is there any schema changes happening on Google BigQuery? Constantly reviewing the access logs of the storage system. So this we will be using to validate and constantly measure Google BigQuery's performance and implementing it. So now, from tomorrow onwards, what we are going to do, tomorrow we are going to get started with making a connection to this BigQuery and start our configuration. Okay, so we'll keep it till here today, where we discussed all these important points. And tomorrow we are going to connect with BigQuery and get started with analysis of our data set.